you ever noticed there's a lot of news stories like this?
A huge lake of salty water has been detected deep beneath the surface of the red planet. And where there is water, there could be life.
Earth-like planet found circling the star that is nearest to our sun. An artist's rendering tonight of what it might look like. They say the planet may have water and ocean. Scientists calling the discovery, quote, amazing.
In a world first, scientists have discovered the first planet with both water and temperatures which could support life. Astrophysicist Brad Tucker joins us from Canberra to discuss this now.
NASA said today a significant source of water was found when it deliberately crashed a rocket into the lunar surface last month. There has been other evidence of water on the moon, but NASA says this is the best evidence yet.
So why does it seem like astronomers are so preoccupied with finding water on other planets? Well, one of the reasons for it is that it's very difficult to imagine how life on Earth could exist without the special properties that water has. Water is very different from most types of liquids. So if life on Earth can't function without water, it stands to reason that if there's a heavy presence of water on a different planet, that might increase the likelihood that life might have developed there as well. As of right now, we've never found life on another planet, but everything we know about the rules of chemistry and biology suggests that it is certainly possible for life to develop on these other planets. And while we don't have a telescope that can directly tell us whether or not life is somewhere, we can detect the presence of water. So what makes water such a special molecule that some of your cells are anywhere from 70% to 95% water? Well, last time we discussed covalent bonds and how two atoms can share their valence electrons in order to form that covalent bond. But in water, the electrons aren't shared equally. You remember that? So the oxygen actually pulls on those electrons a little bit harder. It monopolizes their time a little bit more, and that leaves the hydrogens kind of without their electron that they're donating. And if you recall, the structure of a hydrogen atom is just one positively charged proton and one negatively charged electron. And if we strip away part of hydrogen's electron, that means it's left with nothing but that positive proton. So in a water molecule, hydrogens are positively charged, partially positively charged, and the oxygen is partially negatively charged. And this is what we call a polar covalent bond. It's very important to note that water molecules are bent. You can see that they're at this angle. It almost looks like a little Mickey Mouse face in silhouette, a water molecule does. This top part where you have the hydrogens, that's where all your positive charge is, and then you have this negative part down here with the oxygen. The pull that any given atom has on its electrons is referred to as its electronegativity. More electronegative atoms pull on electrons quite a bit harder, so oxygen's a fairly electronegative atom. Hydrogen is the least electronegative atom. So whenever hydrogen is paired up with something like oxygen or fluorine or chlorine, you can expect there is a polar bond, that there's an uneven sharing of electrons. Now, carbon and hydrogen, they do share pretty evenly, and we'll see some compounds where carbon and hydrogen are involved, and they have nonpolar bonds, but water has a polar covalent bond. And that has an interesting consequence associated with it, because positive attracts negative. So if I have multiple water molecules, say I have a big swimming pool filled with water molecules, they're going to interact with each other. So the positive end of one water molecule will be attracted to the negative end of an adjacent water molecule, and they form what we refer to as hydrogen bonds. Hydrogen bonds are different from other bonds that we've discussed already in that ionic bonds and covalent bonds hold different atoms together to form a molecule, but hydrogen bonds will occur between molecules. So on this slide, you can see we have a number of water molecules arranged together, and the hydrogens from one water molecule are attracted to the oxygen to the one right next to it, but that water molecule itself has a few water molecules that are attracted to various points on it, and every single one of these hydrogen bonds that you see here is pretty weak by itself. But in, say, an entire swimming pool, there are lots and lots and lots and lots and lots of water molecules. So in aggregate, when you add up the force of all of these different hydrogen bonds together, they actually can be fairly strong. Hydrogen bonds are responsible for the surface tension of water. So here you can see a yellow jacket that is standing on the surface of the water, and I love this picture because you can't quite see that the surface of the water is bending under the weight of the bee. Maybe if you squint your eyes, you can see it a little bit. But if you look at the shadow underneath, you see these large circles under every single one of the bee's feet. And the reason for that is that since he's pushing down on the surface of the water, he's creating a little concave space like a lens. And that lens is bending light rays away from those little spots, those little circles below him. So you get these little shadows popping up. You can actually see the distortion of light rays from his effect on the surface tension of the water. Anyone who's done a belly flop knows all about the surface tension of water, because on your trajectory downward, suddenly you hit the surface of the water and smack, you stop your motion entirely all at once, and then you start to sink down again. The reason why it's like you're hitting something solid on that belly flop is all of the energy of motion that you have has to suddenly go into breaking all of these hydrogen bonds between individual water molecules. And like I said, hydrogen bonds are weak, but if you have lots and lots and lots and lots of them, they can actually have a pretty significant effect. The tendency of water molecules to stick to each other is referred to as cohesion. So let's look at a few other consequences of the polar nature of water. Most people know that plants require water in order to do photosynthesis, but consider for a moment, where does that water come from? The water comes from the ground, right? They have to absorb it through their roots, and then that water has to be carried up to the leaves, and the leaves are where the actual photosynthesis happens. But this means that water has to be moved against the force of gravity. It's being lifted up to the leaves. Now, that's not a big task for you or I because, we are animals. So if we want to move liquid from one place in our body to another place in our body, we use, say, our heart, a muscular pump, or we use other kinds of muscles in order to move substances around. But plants don't have that. So how do they accomplish this task? Well, part of it comes down to the cohesion of water molecules. Again, water molecules stick to each other. So the root is dipped down into the groundwater, and it's interacting with these water molecules, and some of those water molecules will be absorbed into those roots on these little kind of projections called root hairs. Once in there, they will find all of these tubes, and the walls of these tubes are also able to hydrogen bond with the water molecule. So when you have water molecules sticking together, that's cohesion, but when the water molecules stick to something else, it's called adhesion. And as each water molecule is looking for places to bind onto, they might move just a little bit up in this tube, and it's going to pull all the water molecules below it along with it. So slowly but surely, they start walking their way up the sides of these tubes. You've seen a similar kind of response if you've ever taken a napkin and you've dipped it into a glass of water, or maybe you're just cleaning something up and you see the water kind of get pulled up against the force of gravity into the little spaces in that napkin. This is referred to as capillary action, and it's a result of hydrogen bonding. Once the water has been carried all the way up the xylem, that's the plant tissue that's transporting them, they get up to the leaves, and there's some evaporation that occurs at the leaves. Water is going to escape into the gas phase, but as it does, it continues pulling on those water molecules just behind it, which means that the process of evaporation up at the leaves is actually pulling more and more and more water molecules out of the ground. An interesting consequence of this is that trees effectively allow groundwater that might not have evaporated on its own to escape back into the atmosphere. So they become rain machines. Like, we call rainforests rainforests because it rains a lot there, but in a very real way, the forest is a big rain machine. The reason why this is so important, though, is because photosynthesis is the source for all chemical energy in ecosystems. Every bit of energy that you get out of the food you eat, ultimately it was captured by plants. Capillary action is what allows land plants to do their photosynthesis. And without land plants, think about every single fruit and vegetable in the supermarket that you could eat yourself, and think about all of the plants that we feed to the animals that we as a society eat as well. They're all land-based plants. So without capillary action, all of that kind of melts away, which makes this a pretty important outcome of the properties of water. At the top of our next slide, there's a couple of words that you're probably going to want to memorize as soon as you possibly can, and these are hydrophobic and hydrophilic. So what does this have to do with the properties of water? Well, Some molecules are what we call hydrophilic molecules. They are water-loving molecules. Hydro, water, philia means love, so they are water-loving molecules. What kinds of molecules are these? These will be any kind of ion, so any atom with a positive or negative charge that has, one too many or one too few electrons, causing it to have an overall charge, and any other molecule that has polar covalent bonds like water does. Because water is a polar molecule, because it can form hydrogen bonds, it is attracted to any kind of molecule that has even the slightest hint of a charge on it. And this means that there are a wide variety of molecules that will dissolve inside water, that you can mix up inside of water. So we say water is a very good solvent. And you may remember me mentioning solvents before, when we were talking about collision theory, ways to get molecules to kind of collide with each other more frequently to get better chemical reactions. Well, one way you could do it is to put these molecules into a liquid medium so that they're more freely able to move around, and that will help your chemical reactions proceed forward. And since your cells, again, are mostly made out of water, there are lots of chemicals that can bump into each other just floating around inside of your cells. So when a molecule can dissolve inside water, when it can mix with water, we say that it's hydrophilic, and sodium chloride is a good example. Now, there are some molecules that don't mix with water, like oil and water, right? You guys have seen oil and water before. If you pour some oil into just a container of water, the oil will sit right on top of that water because, one, the oil is actually lighter, it's less dense than the water, so it will sit on top. And two, they don't mix well with each other. They aren't attracted to each other at all. And the reason for that is that hydrophobic materials have no charge overall on them anywhere. They don't have a full ionic charge like the sodium or the chlorine atoms, and they don't have any polar covalent bonds like you would find inside water or alcohol or any other kind of material where there's an unequal sharing of electrons. We'll talk about nonpolar substances a little bit more later when we discuss lipids, and the idea of hydrophobic versus hydrophilic will be very important when we start talking about the cell membrane in Unit 2. So keep these terms in mind, but for right now, let's take a look at water as a solvent. So let's say I get some salt and I mix it up inside of a glass of water. Eventually, it starts out with all these little grainy crystals of salt, but eventually those crystals are going to just kind of disappear. And the reason why they do that is that a salt crystal is made out of these sodium and chlorine atoms. Many, 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 many atoms to be big enough that we could actually see these crystals with our naked eye and we can hold them on the tip of our finger, but they are ultimately made out of just these two materials. So as I'm mixing it around in the water, I'm exposing more and more of the surface of these crystals to the solvent, to the water. And wherever you have a sodium ion, remember sodium is a positive ion, it is a cation, the negative side of the water molecules, the oxygen end, are going to be attracted to that sodium ion. Whenever you have a chlorine ion, a chloride ion, it's going to be attracted to the hydrogens on the water molecules. So what does this mean? This means that even though hydrogen bonds are very, very weak, because there's so many water molecules, they can add up all of that strength, and you can actually get a more powerful attraction between chloride ions and the water molecules surrounding them than they are attracted to the sodium. So the water starts pulling individual ions, individual atoms out of this salt crystal, and they get mixed up. And you can see that they form a little bubble, a little sphere of water molecules around each of these ions, which then would prevent them from coming back together, because before chlorine and sodium can form a new bond, a new ionic bond, they would have to get all of these water molecules out of the way, and the water molecules are very happy to be attracted here. So this helps dissolve this material. It helps dissolve salt crystals inside of the water. So when we say that water is a solvent, we mean that you can mix materials up in it, and they will just be kind of floating around inside the water. So just a little bit more vocabulary here. You'll want to know this when we get into lab, and I'll just be using these terms throughout. Whenever we dissolve one substance inside of another substance, what we're doing is making a solution. In science, we refer to a mixture as a solution. And in a solution, you have two components, the solvent and the solute. In this scenario, water is the solvent and the salt crystals, the sodium and chloride ions, are the solute. They're what's getting mixed up. but just about anything can be a solute. You could have sugar molecules, right? We can make up some sugar water, and that could be a solute because that can mix very, very well. Typically, the solvent is just whatever material you have more of. So if we're mixing two liquids together, which one's the solute and which one's the solvent? Whichever one I had more of to start with. All right, so properties of water we've talked about so far. Cohesion and adhesion lead to capillary action. Then we have water acting as the solvent of life, so it's very important in chemical reactions. Next, water has what we call a high specific heat. What does that actually mean? It means that water can absorb lots and lots and lots of thermal energy, lots and lots of heat, while only changing a few degrees in temperature, which is great if you're an organism like us who's interested in maintaining their body temperature, interested in maintaining homeostasis, which you'll recall is one of those criteria of life. Because water requires so much energy in order to change its temperature, it either has to lose a lot of energy to reduce in temperature, or it has to gain a lot of energy in order to increase in temperature, that helps us keep our bodies stable. It helps keep our cells at just the right temperature. And hey, it also helps keep ecosystems at just the right temperature, and the Earth in general. Water is a greenhouse gas, so having some water vapor in the atmosphere is actually why we're able to retain so much heat. And I would be willing to bet that most likely many of you have had interactions with water where this high specific heat has been demonstrated. Give you a couple examples. A watched pot never boils, does it? That's what my grandmother always told me. A watched pot never boils. And really, what she's saying is that it just takes a very, very long time for a tea kettle to come up to the right temperature. Now, if you have another type of liquid, say you put some oil into a frying pan and you turn up the heat, that oil gets hot and ready to fry pretty darn fast, but water takes forever to increase in temperature. Well, that's because of this high specific heat capacity. And the reason for that is that temperature is a measurement of the kinetic motion of molecules. So the more molecules are moving around, the warmer the temperature is. But because of the hydrogen bonding, when water molecules gain energy, that energy has to first go to break the hydrogen bonds between water molecules before it can be used to have them move around and kick all over the place. So the hydrogen bonds again give water this property. Another way you could look at it is that it takes water a very long time to lose energy. So if you've ever been on vacation, or maybe you own a swimming pool, if you've ever had a situation where it's hot summer day, there's a swimming pool and it's warming up in the sunlight, and then the next morning you decide to go out for a dip in that swimming pool. Now the air is really cold in the morning, but you go into the swimming pool and the water is so warm still. In fact, there's steam coming off of that swimming pool, isn't it? It's still warm from the day before, because not only does it take a lot of heat to raise the temperature of water, it also takes a very long time for water to lose that temperature once it has been gained. So we call this a high specific heat capacity. Now, if you don't have too much experience with those other two examples, I'm almost certain that you have experience with sweating, which is one way that our bodies go ahead and try to moderate our body temperature. When you are overheated, your body starts venting water out onto the surface. And as that water is sitting on your skin, it's absorbing a little bit of the heat from your body. But then that water evaporates away. And when it evaporates away, it takes the heat along with it. Imagine the hottest water molecules, the ones with the most energy, as the fastest runners on a track team. And if we take all of the fastest runners off of the track team, the average speed of the entire team goes down. If we remove all of the hottest water molecules from this sweat droplet, the average temperature of the droplet decreases. So you end up with evaporative cooling. One last property of water that I want to mention is that frozen water floats. Ice floats. You put some ice cubes into a cup of water, they're going to float right on the top. Now, I know that is not like a profound statement. You're thinking, okay, yes, ice floats. Of course it does. That's not, earth-shattering. But it kind of should be, because that's not how virtually any other material on the planet behaves. The solid version of matter usually is more dense than the liquid version, so the solid should sink inside the liquid. But water is the exception to this rule. It doesn't behave in the way that you would expect. And the reason is, and this is going to shock you, hydrogen bonds. The hydrogen bonds between water molecules attract those water molecules together, yes? But When water has enough energy to be liquid, the water molecules can move around, right? They can wiggle out of place. So they can break those hydrogen bonds a little bit more easily, which means that they can kind of drift close to each other and far away from each other and close to each other and all over the place, constantly establishing and breaking hydrogen bonds on a second-by-second basis. But as we remove energy, as we remove temperature from this liquid, suddenly they don't have the motion required, the amount of energy required to break those hydrogen bonds. So the hydrogen bonds dominate. They are the main thing that is determining the location of every molecule of water. Most other types of materials, right, okay, we have no temperature, so we're just going to kind of all cluster together. But water molecules, because of those polar covalent bonds, they play tug of war with each other. So you have one water molecule pulling this direction, and another one pulling this direction, and another one pulling this direction, and every water molecule has that same set of forces pulling it every which way, which causes them to spread out. And if they spread out, they're taking up more space, even though they have the same amount of stuff there. And that means less density. And less density means that it's going to float, just like a boat floats, because it's less dense than the water it displaces. Frozen water is less dense than the liquid water it is displacing, so frozen water floats. Now, why is that important to biology? Water is where life developed in the first place. So life started in the oceans, near as we can figure. That could not have happened if frozen water sank, and here's why. Imagine a pond, say. So it's a depression in the ground, and there's water in this depression, liquid water here. The way it currently works is that first, when we get to winter, the air temperature is going to drop, right? That's going to drop first. And then slowly the water will lose some of its heat to the air, so the temperature of the water will go down, but not all in a uniform way. The water molecules at the surface of this pond are going to lose their temperature first, because they're right there next to the cold air. So they're going to start to freeze over first, and frozen water floats, so they stay right there at the top, and you get this layer of ice that develops, this crust of ice over the top of the pond, and the rest of the water remains liquid, because as it turns out, ice is a pretty darn good insulator as well. So you get this nice little liquid water environment that is underneath the frozen ice all year round. And that will allow life to thrive. You need liquid water to circulate oxygen around your blood. You need liquid water in order to be able to move around. If you're a block of ice, it's really hard to have any kind of metabolic processes proceeding forward. Now, let's imagine a universe where frozen water is more dense than liquid water, so ice sinks. Same thing will happen. Air temperature decreases at the surface, and that's going to freeze the water molecules at the top, but now they sink. So this little bit of ice that just formed, it's going to sink to the bottom of the pond, which means there will be new liquid water up at the top, and then that will freeze, and then that will sink, and then new liquid water will freeze, and then that will sink. And it would actually be almost like it was snowing inside this lake, little ice crystals constantly trickling down, falling down to the bottom. And then you get this solid layer of ice at the bottom of the lake, and it would actually freeze from the bottom up. Eventually the liquid water, all of the liquid water would be displaced to the top, and then you would have it frozen solid. So the entire lake will be a solid block of ice. Now you can take that idea and expand it out to like the entire ocean. So all water on Earth would be frozen over during the cold season. And then when summer comes around, okay, we're going to start heating this up. We have this massive block of ice. And what did we just learn about water? It takes a lot of energy to get water to change its temperature. So only the very, very top layer, the surface of the water, would actually melt, and then it would refreeze again. It's very difficult to see how life could develop on a planet where all of the water is essentially frozen solid year-round. So the fact that frozen water floats, it is one of the vital traits of water that make it important to life on Earth.